Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review the Pearson correlation and fitted line plot tests that measure a relationship between two factors. I'll spend the first part of this lesson reviewing some of the critical concepts that can help you to understand how to use these tests. But despite that, I recommend that you at least review the prior lessons on hypothesis testing if you haven't already done so. But for now, let's review again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's review again the various steps we follow when doing hypothesis testing.
On a high level, the steps begin with a four-step process, which was starting with a practical problem. We're stating the problem as a yes or no question, and then we want to convert that problem into a statistical problem. That's going to help us to figure out which is the right statistical tool or method we're going to use to help figure out how we're going to do the analysis. And then we apply that statistical tool or concept on it, and then we interpret the results from that and come up with some analytical answer. And then from that, we would interpret the analytical answer into some practical solution or some practical way in applying that so it makes sense to us. And at the heart of doing the hypothesis testing, again, for steps 2 or 3, that's where we drill down to 6 additional sub-processes or sub-steps in order to figure that out. So it started off with defining the objective. Then we want to state the null and the alternative hypotheses. Then we define the confidence level and the power levels based off of the alpha and beta risks that were identified. Collect the sample data, and we want to calculate the p-value. All these are part of building this statistical problem. And then once we've done that and run the test, then we interpret the results. This is going to be the point where we decide whether we're going to accept or reject the null hypothesis. This is what we'd follow when we want to go through the formal hypothesis testing.
All right, now let's review again the chart for finding the right statistical test and where the Pearson correlation and fitted line plot fit into all this.
Well, as we look again at the familiar drill down for finding the right statistical test, again we started off with asking the question, is the data type for both values that we're comparing, is that data type continuous for both of them? And when they both are, then we'll find ourselves going down this path for doing relationship types of testing. And when we're comparing two values, one with each other, then the type of test we can use in this example would be a Pearson correlation or a fitted line plot. And those are the tests that we're going to be going over in this lesson.
Okay, now let's talk about how to run the Pearson correlation test from within Minitab.
Well, we would run the Pearson correlation test when we have two continuous values that we want to compare with each other to see if they're correlated. So for a Minitab, what you would do is go to the Stat menu, select Basic Statistics, and choose Correlation. Now in this particular test, the dialog box is going to look like this, and normally you would at least select two values that you're going to be comparing and running the correlation on. However, what's really cool about this kind of test that I'll show you is how you can select more than one continuous value and dump them all into the list of variables. Now we're still only comparing one value at a time, but what I'll show you is if you add multiple, more than two, of the variables within this box, then it will create a matrix for you that runs all the cross possibilities between all the variables that you select.
All right, now let's walk through an example using the Pearson correlation test.
Well, in this example, we're going to have several values that we're going to be plugging in. So we'll go back to the Minitab sample data file that's provided on the website, and we'll just select arbitrarily the different continuous values that are available within that file. So for the practical problem, we're going to ask ourselves, is there a relationship between any of these continuous values? And if there is a relationship between them, then how strong is that? Now, the statistical problem that we'll translate that into is, first we've got to start with stating the null and alternative hypotheses. So here's a rough example what it might look like, where the null hypothesis is where we're looking at the row value is equal to 0 for the first group, and for the second group it's also 0, and the third group we're looking at is also to 0. Or you could say the R value is equal to 0 as well, whether it's a population or sample that we're looking at. The alternative is that we're saying it's greater than 0. We're actually something different than 0. So we're basically saying anything that exceeds 0 for the correlation coefficient for any of these sets of values, we're going to presume that they are correlated. So we're going to also define the confidence and power levels. So for the confidence level, we'll use the default of about 95%, which means alpha is 5%, and the default power level of 90%, which again means the beta value is 10%. And we're going to type the statistical problem in Minitab. Where in Minitab we're going to go to Stat, Basic Statistics, and Correlation. And in the Variables box, let's select all the continuous values, which are metric A, B, C, D, and E from the list of columns that are available. Now for the statistical solution, the results when we run it, it's going to look something like this in the output from the session window. So what do we do with this information? What does it mean? Well, each of the continuous values that we plugged into there is tested against every other continuous value, and the correlation coefficient and p-value are also noted for each test. So if you notice, it tells you at the top, here are the 5 different variables that we ran this test against. Now remember, this particular test we said is only comparing one value with another. Since it's only running 2 values at a time, one against the other, then what it does is it takes the first 4 parts of the 5 metrics that we're plugging in here, metric A, B, C, and D, and we're comparing it with the other 4, metric B, C, D, and E. So in this case, we say in this cell right here, here's the comparison of metric A and metric B, and we get these results and these contents, and this what it's calling a cell. Then it compares metric A to metric C, and we get these results. Then metric A to metric D, get these results, and so on, all the way through all the other ones. So metric B, here's comparison to metric C. This one's blank, obviously, because I don't do metric B to metric B. And so that it wouldn't matter in that case. And same thing here, metric C to metric B, well, that was already run here. So it looks like this, and how it does the comparison, all the possibilities across these variables to find the results of whether there's a correlation or not. The way to interpret each of these sets of cells too, it tells you at the bottom the p-value is the value that's beneath each one of these. The Pearson correlation, or that correlation coefficient, is the upper value within each of these contents that are listed here. So what do we do with this? Each test is going to align with a row or column for the metric values, and as an example, we'll say we're comparing metric A to metric C. It has a p-value of 0, and the correlation here is 79%. Then we might compare that to another comparison of metric B to metric D. In this case, the p-value is about 24%, or 0.237, and the correlation is actually 12%. So in this case, this is how we interpret it, as we normally do. We look first for the p-value, and after we look at the p-value, that's where we compare it with the correlation coefficient that's gives in the results. So what do we do with this as a practical solution? Well, first of all, what combination of metrics have a correlation? When we ask ourselves that, again, we got to look for the p-value first, like we do in every test, using the same confidence and power levels that we've done before. So in this case, it looks like metric, if we start from the top here, there's no correlation there because the p-value is so high. Here for metric A and metric C, it's a low p-value, so there is one there. There is one here, it's low p-value, so there's some relationship between those. It doesn't seem to be any for these because the p-values here are much greater than the alpha risk we're willing to accept, or even the beta risk that we've identified. Here in this case, again, p-value is 0, so that one we would say does have a correlation. Same thing here and here as well. So we look again for the p-values first. So what combination has the strongest correlation? Now among those that have a p-value that's very low, where we can say there is a correlation, that's where we look for the correlation coefficient itself. So you can see some of these are very high. Here's a 97.4%, and here's one at 99.9, so it's nearly a 100% correlation between this. This is probably the highest among them. Now, which of these might be the weakest? Again, we'd only look among those that actually have a correlation. That is where there's a low p-value. So all these other ones I can ignore because the p-value is just too high to accept the risk. So here's one at 79.7%. It's a little bit lower. And here's another one at 79.3%. Well, this is probably, among the examples that are provided here, this is probably the weakest correlation between them, because again, it does have a correlation, it's a low p-value, and here's the correlation coefficient, which tends to be the lowest among all those that were compared here.
Okay, now let's dig into the fitted line plot and how to run it from within Minitab.
Well, we would run the fitted line plot when we want to build a regression equation by comparing the two continuous values to see how correlated they are. We want to give ourselves the result of an r-squared value, or r-squared adjusted. So how do we run this within Minitab? You go to Stat, then Regression, and select Fitted Line Plot. Now, what are the inputs for this test? Well, this is the kind of dialog box that we're going to be getting when we select the fitted line plot. And then we just plug in here the two values that we're comparing, the y value and the x value. And then I would also recommend selecting the Graphs button, and from within here choose the 4 and 1. This is going to give us the residual plots, and we'll get to that in a second of how you interpret that. Then also select the Options button, and from within here I would recommend selecting these two options where you display the confidence interval and the prediction interval. Again, we'll get to that in just a second, but these are important options that might help you in how you'd interpret the information within the fitted line plot.
Alright, now let's walk through an example of applying the fitted line plot.
This example is going to be using metric A and metric B as our sample values. For the background, we're saying that we're going to be drawing from the Minitab sample data file that's provided on the website. We're going to be using the arbitrary values represented in the metric A column and the metric B column. So the practical problem we're going to be trying to answer here is there a relationship between the metric A and metric B? If there is, then how strong is that relationship? So our statistical problem we're going to translate that into is stating first the null and alternative hypotheses, where the null hypothesis is where the population correlation is equal to 0, indicating that there is no correlation between the factors. And the alternative is that there is some sort of relationship, that is, the correlation is greater than 0. Now we're also going to define the confidence and power levels, where we'll use the default where the 95% is our confidence level and the power level of 90%. And then for the statistical problem, how we create it with the Minitab, we're going to go to the Stat menu, select Regression, and choose Fitted Line Plot. We're going to select metric A as our response value, the y factor, and then metric B is the predictor, the x, from the list of columns that are available. And click on the Graphs button, that's where we're going to select 4 and 1, and then click on the Options button and we'll select Display Confidence Interval and Display the Predictor Interval. Now as we run the test, the statistical solution is going to look something like this, where we have this kind of output created from within Minitab session window. In this case, when we refer to these results, we'll see that the p-value that's provided for us is greater than our alpha risk of 5%. In this case, the p-value is 0.302, which is about 30%. Since this p-value is greater than our alpha risk, then we're going to fail to reject the null hypothesis, which is essentially the same thing as saying we're going to accept the null hypothesis, which says that there is no relationship between the two factors that we're comparing. So what does this really mean from a practical standpoint? Well, we're saying that the sample that's provided is insufficient to prove that metric A is correlated to metric B. Therefore, in that case, the r-squared value that's provided here in the results is irrelevant. Because the p-value is so high, it doesn't matter what the r-squared value is. However, if our p-value was low, less than our alpha risk that we identified, then we could trust what the r-squared value is. In this case, if we did, if the r-squared value is so low, it's close to 0%, that we probably wouldn't even say there's a relationship anyway, even though statistically we might say that the risk is low. But in this case, that's not the case. R-squared value is so low anyway, it's probably because we have a high risk and our p-value is as high as it is. So if there were a correlation, though, between the variables that we're comparing, then we could also rely on this upper value that's part of the results that's created in Minitab, where it creates that equation, the regression equation. This is where we're saying metric A, the output y response, is equal to this constant, 487.9, plus this coefficient, 96.39, multiplied by metric B. This is the kind of equation that we'd be looking for. Had we been able to have a p-value that's low enough that we can trust the results from this, and it looks like there's a strong enough correlation for us, then we could probably use this type of regression equation in order to do forecasting and testing our values, where we just simply plug in the variable like for metric B, and then solve for the equation to tell us what metric A probably will be. Or we can do the reverse if we're trying to solve for metric B instead and just adjust the equation to account for that. But either way, this is the kind of equation we're looking for when we have a regression that we can trust. In this case, we can't because the p-value is too high. But next we're going to look at the results for the from this test, where we're going to look at the 4 and 1 for the residuals, as well as look at the confidence interval and the predictor intervals displayed in the output from the fitted line plot.
Now let's explore an important aspect of the fitted line plot, and that's the confidence and predictor intervals.
Well, as we remember, we'll go over the concept again of confidence intervals, and we use those as an estimate of a range around a mean. So the predictor intervals are similar, but they give a range for predicting future data points or observations that we're looking at. So as a reminder, like we talked about before with confidence intervals, when you have fewer samples, the actual confidence interval itself will be kind of wide like this. The population mean we're saying is going to fall within this wide interval. But as we collect more samples, the interval itself narrows a little bit more. And that way we're still saying that the population mean is going to fall within this, but now that we have more data, we can have more confidence that we have a tighter range for we can predict where the mean is going to fall. And as we collect more and more samples, again, the more narrow that interval becomes because we have more data to give us confidence that the actual population mean is going to fall within this more narrow window and this range that's provided. Well, it kind of works the same way when we talk about confidence intervals and predictor intervals within a fitted line plot. So when we have the fitted line plot that's created and we add that option of adding the confidence interval and predictor intervals, it's going to look somewhat like this, where you have the green and red dashed lines that are added to the plot itself. Well, the red dashed lines over here, those represent the confidence interval. It's where we're saying that's the fitted line for the mean, should it fall within that range for the population. So you can see this is where the line is drawn, and if you have the population, we're saying that it's going to fall, there's a 95% confidence it's going to fall within this narrow range, this narrow interval where the red dashed lines are represented. Now the green dashed lines that are represented, that's the predictor interval. And it's the same kind of concept where it's 95% confidence that the population is going to have observation or data points that fall within the green lines. Obviously we have a few falling out, but it's generally saying that with 95% confidence that future data points are going to fall within that much wider range.
Okay, now let's review again what are residuals and how we can interpret them in Minitab.
Well, to answer what are residuals, if you recall, we'd say a deviation is the distance a data point is from the mean, how far each of those different observations are from the mean, or that average. Well, for regressions, residuals represent the same kind of thing. It's a deviation of each data point from the line that's being fit among the values that you're comparing. So in this example, if we have a plot like this, and we have the line that's fit between them, we would say that the residuals measure the deviation of the fitted line. So it's looking at the distance the data points are from the line, and that's what would represent the residuals, how far apart they are from the line that's being fit. So how do we look for the residuals? When we create that graphs option to look at the 4 and 1 within Minitab, when we call up the fitted line plot, what is it that we're looking for in the residuals and the type of results? Well, for the residuals, we expect that they'd have certain characteristics. First of all, we expect that those residuals would be normally distributed, that the distance for each of these would be normal. It doesn't matter whether the continuous value that we're looking at is normal or non-normal. Even for non-normal distributions, when it tries to fit a line, it doesn't matter. It should still represent a normal distribution for these deviations or these residuals. So we'd expect that when we look at the characteristics of the residuals. As well, we expect them to be independent, and they should have equal variances. So this is the example of the 4 and 1 graph output that comes from a fitted line plot. So in this example, on the far left two charts, we would look for the distributions to see if they look to be normal. In these examples, they look relatively normal, especially when we look at this normality plot. And then we look up here to see, are the spread of plots on either side of the line look similar. So they look like they're evenly distributed on either side of the center line. And also we look over here for the spread of the plots. They should look random, like there's no pattern or trend among them. And it looks like, according to this, there isn't much of a trend at all. They seem to be well distributed across this and very random.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to those metrics that you identified as part of this whole hypothesis testing that we're looking at. And for any of the values that are continuous values, then try to apply some of this Pearson correlation or the fitted line plot. And then for any other factors you might have in your organization that you want to test as well, feel free to include this as part of the exercise. Now, before you run either of these tests that we're looking at, ask yourself, do you expect there to be a relationship between the factors? And if so, how strong would you expect the relationship to be? Then run the test, and after running either of those tests, do you see that there is a statistical relationship between them? And if so, how strong did the test come out to show? If the answers between the last two questions are different, then how does it affect how you typically measure and communicate the relationship of those factors from within your organization? So as an example, does the relationship between the factors that affect some financial decisions that are made, or maybe some process changes or other kinds of critical actions that might be necessary in your organization? If so, then how should the results from this test be used to influence your organization? Is it something that should change how the factors are being compared, like across different times, locations, or groups? Or should they change how the factor is being measured? Or maybe should it change how they react when they compare the metrics in this way?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.